Have you ever just looked around and wondered what all this stuff is actually made of? Well, today we're going to peek behind the curtain into the secret world of, well, stuff. We're going to figure out what connects the phone in your hand to the air you're breathing right now.
Seriously, take a look. Your screen, your desk, maybe a cup of coffee, they all look and feel completely different. But what if I told you that deep, deep down, they're all made from the same basic recipe? You know, scientists have a pretty simple word for all this stuff. They call it matter. And the rule to be in the matter club is super easy. If it has mass, if it has some weight to it, and it has volume, meaning it takes up space, then congratulations, it's matter. A tiny speck of dust, the biggest planet, it's all matter. So what is this matter really? For centuries, people wondered, is it one solid, continuous thing, or is it made of countless tiny little bits? Well, we're going to solve this ancient mystery right now with a little something I like to call the case of the disappearing salt. Okay, picture this in your head. You take a glass of water and you draw a line on the side, right at the water level. Now you take a spoonful of salt, dump it in, and stir until it all dissolves. Poof! It's like it just vanished. But here's the really weird part. You look back at that line you drew, and the water level hasn't gone up at all. We know the salt is in there, but the total amount of space being taken up is the same. So what gives? Where did the salt actually go? And here it is, our aha moment. The salt didn't disappear. It just broke down into pieces so incredibly tiny that they could slip into the gaps that were already there, right in between all the water particles. This proves it. Matter isn't one solid block. It's made of tiny particles with empty space between them. All right, so case number 1 is officially solved. Matter is made of particles. But that just opens up a brand new question. Just how tiny are we talking here? Let's try another little experiment. If you take just a couple of tiny purple crystals, the stuff is called potassium permanganate, and dissolve them, the water turns a deep purple. Now get this. You can take just a tiny drop of that water, add it to a new glass of clear water, and the whole thing still turns pink. And you can do it again, and you'll still see a hint of that color. Think about what that means. For the color to spread that much, those first few little crystals must have been made of millions of individual purple particles. The scale is just mind-boggling. As our source material puts it with the perfect amount of excitement, the particles of matter are very small. They are small beyond our imagination. And they're not wrong. Now, on top of being tiny, these particles have another secret. They are never, ever still. They are constantly vibrating, wiggling, and zipping around. This movement is called kinetic energy. And when you add heat, you give them a shot of espresso. They start moving way, way faster. It's exactly why you can smell hot food sizzling from across the room, but you have to stick your nose right up to a cold sandwich to smell it. Those hot particles are literally flying through the air to find you. So we have these tiny particles that are always on the move. The next piece of the puzzle is figuring out how they act when they're all together in a group. The way they stick to each other and move around is what gives us the 3 states of matter we see every single day: solids, liquids, and gases. This chart really breaks it down. In a solid, think of the particles like bricks in a wall. They're locked into a fixed pattern, so the solid keeps its shape. In a liquid, it's more like a ball pit. The particles are still close together, but they can tumble and slide past each other, which is why a liquid takes the shape of whatever you pour it into. And a gas? Oh, the gas particles are just going wild, flying around freely and bouncing off everything. They'll expand to fill any space you give them. I know what you might be thinking, though. What about those weird solids, like a rubber band stretches, right? Yep, but it's a solid because it snaps right back to its original shape. Or sugar. It pours out of the bag like a liquid. But if you look close, every single grain is a tiny, perfectly shaped solid crystal. And a sponge. It feels squishy, but you're not actually compressing the solid sponge. You're just squeezing the air out of all the little holes inside it. So, we have our 3 states, but of course, they aren't permanent. We see matter change states all the time, like when an ice cube melts or water boils into steam. So, how does that work? How do we force matter to change its state? Well, the secret ingredient is almost always energy, usually in the form of heat. All right, let's head back to the lab for a second. Imagine a beaker that's just full of ice. We pop a thermometer in and it reads a chilly 0 degrees Celsius. Now we start to heat that beaker up from the bottom. So the ice starts to melt, No surprise there. But here is where something really strange happens. Even though we keep adding heat, the thermometer's reading doesn't change. It stays stuck right at 0 degrees Celsius until every last bit of ice has turned into water. So if we're pumping in heat, but the temperature isn't going up, where's all that energy going? The answer is a really cool concept called latent heat. The word latent just means hidden. So this heat is there, but it's hidden. Instead of making the particles move faster, which is what a thermometer measures, all that hidden energy is being used for one specific job, to break apart the bonds that are holding the water particles together in that rigid ice crystal structure. Now, this is the wild part. It means that particles of water at 0 degrees actually have more energy than particles of ice at the exact same temperature. They've absorbed all that hidden heat just so they could break free. And that's why a glass of ice water feels so much colder for so much longer than a glass of plain cold water. And this hidden heat comes in two main flavors. The energy you need to melt a solid into a liquid, that's called the latent heat of fusion. The energy you need to turn a liquid into a gas, like when you boil water, is the latent heat of vaporization. And let me tell you, it takes a lot more energy to vaporize something than it does to just melt it. Okay, this is some cool science, but how does it actually affect you in your day-to-day life? Well, this whole idea of hidden heat is the secret behind one of your body's most amazing tricks, cooling itself down. Try this quick thought experiment. Have you ever put some nail polish remover, which is mostly acetone, on your hand? Or maybe some rubbing alcohol? What's the very first thing you feel? It feels cold, right? Instantly? So why does that happen? It's all about evaporation. For those liquid particles to escape and turn into a gas, they need energy. They need that latent heat of vaporization we just talked about. And where do they get that energy? They steal it. They pull the heat right out of your warm palm. And since your hand is losing heat, it feels cold.
This principle is working all around us all the time. It's exactly why sweating cools you down. As the sweat evaporates, it pulls heat away from your body. It's why we wear cotton in the summer. It's great at helping sweat evaporate. It's even how an old-fashioned clay pot, or a matka, keeps water inside it so cool. Tiny bits of water seep through and evaporate off the outside, cooling the whole pot down. It's like nature's own personal air conditioner. So from a disappearing spoonful of salt to the reason you feel cool after a swim, it all comes down to the secret life of these tiny, energetic particles. We've explored solids, liquids, and gases, the states of matter that define our world. But it kind of makes you wonder, what other more extreme states are out there? Like the super hot electrified plasma that powers the sun and all the stars. Now that is a story for another time.